physics fans. It's Mr. G here today to talk to you about the second type of energy we'll talk about in this unit, and that's this idea of kinetic energy. You'll see a picture of the guy on a nice little rocket bike there, definitely showing that there is some motion involved, and wouldn't you know it, kinetic energy is all about this idea of moving objects. So kinetic energy, the most basic definition is this idea that it is the energy of moving objects, and like potential energy, it is a scalar value measured in joules. In this case, however, we have an equation where the kinetic energy is equal to 1/2 mv squared, where m is still the mass and v now is the speed. I want to make it very clear that it is not the velocity, but is in fact the speed. So remember, speed has magnitude but no direction, velocity has both. Much like potential energy, an object, regardless of direction or motion, has an inherent energy, and the same holds true for kinetic energy. As you'd find out in university, the reason this is the case is because it's actually a dot product between the two velocities, which cancels out the direction altogether. You can deal with that first year university. So with this equation, we can do some things with it. So let's take a look. A 60 kilogram student is running at a uniform speed of 5.7 meters per second. What is the kinetic energy of this student? Well, we just learned that the kinetic energy is equal to 1/2 mv squared. We're given a mass, we're given a velocity, so this is a simple plug and chug. So this is 1/2 times 60 kilograms times 5.7 meters per second squared. And if we crank that out, we should end up with about 575 joules. So notice again, I'm always using SI units. And if you do so, you should end up with an answer in joules. So that's the first example. Let's take a look at a different example now. Let's say that the kinetic energy of a 2.1 kilogram rotten tomato is 1,000 joules. How fast is the tomato moving? Well, as soon as you hear that we have a moving object and you're given the energy, we go right to kinetic energy equals 1/2 mv squared, except this time we're trying to look for how fast the object's moving. So we actually have to solve for v. And for those of you that have been practicing your algebra, you should end up with velocity equals the square root of 2 times the kinetic energy divided by mass. Plug in our values and we get the square root of 2 times 1.0 times 10 to the 3 joules divided by 2.1 kilograms. You'll notice again that the square root is over both quantities, not just the numerator or denominator. But if you do that, you should end up with a number of 31 meters per second. When you're going through kinetic energy type problems, make sure you check to make sure that the units of the velocity are exactly what the question is looking for. Sometimes it doesn't tell you, in which case leave it meters per second. Other times it will tell you that it wants it in kilometers per hour or something else. All right, well, with the kinetic energy, there is a very, very useful theorem relating kinetic energy to work, and it's called the work energy theorem. And it works a little something like this. If a net force acts on an object, then it must be accelerating. Duh, you learn that from dynamics. That should be no surprise to you. But in this case, the acceleration is proportional to its change in kinetic energy. An object is in motion. There's got to be forces at play. We are able to relate the two together with this equation right here. So you'll notice that work is equal to the change in kinetic energy, which is equal to, in this case, F net times distance. So remember, with potential energy, we were dealing with things, or rather with the work equation to begin with, we dealt with things that were with the applied force. But now we're saying, let's go right to the net force. And let's take a look at how that's used. A sprinter exerts a net force of, so again, net force of 260 newtons over a distance of 35 meters. What is the change in kinetic energy? Well, we know that work is equal to the change in kinetic energy, which is equal to our F net times distance. And if we put that in, we have 260 newtons times our distance of 35 meters. Everything was in SI units, so this is exciting. And you end up with a value of 9,100 joules. So really important to remember this connection here, which then leads to F net times D. Again, pretty much a plug and chug situation. Let's take a look at something a little different. A student pushes a 25 kilogram crate, which is initially at rest, with a force of 160 newtons over a distance of 15 meters. You got distance, you got some sort of force, and we know that it's moving because it's being pushed. If there is 75 newtons of friction, what is the final speed of the crate? So this one's a little trickier, but again, we're going to start off with work is equal to the change in kinetic energy, which is equal to F net times distance. Our change in kinetic energy, though, you may remember, is the same idea as the kinetic final minus the kinetic initial. But if we think about it, we're talking about something that was initially at rest, so the initial kinetic energy has to be 0. Plug in 0 in for V, you get a value of 0, which means that this simplifies to 1/2 mv final squared has to equal F net times d. Well, at that point, this is straightforward again. It's another algebraic situation. So take our final velocity has to be equal to the square root of 2 F net times d, and that's going to be divided by our mass. And if we plug in the values, we should get the square root of 2 times 85 newtons times 15 meters divided by 25 kilograms. And if we've done everything right, we should end up with a number of about 10 meters per second, depending on if you deal with sig figures or not. I don't. That's a chemistry issue, not mine. So there we have it, folks. You've seen kinetic energy at work. You've seen the work energy theorem, which is super useful. For the most part, once you set up the equation, you're good to go. So good luck, my friends. Enjoy the rest of your kinetic energy experience.